all for being here. I'm Caroline. I'm a senior at Appalachian State University, and I'm majoring in mathematics and also pursuing a certificate in GIS. And I'm really excited to present to you this project I did on exploring characteristics of community resilience using a logistic regression model. So we first started off with getting a definition of resiliency. We adapted it as being the ability to withstand and adapt from disturbances such as climate disasters. And we put this in a community context. And the goal of the project was to determine variables that associate with resiliency and also create a model that would predict areas of high and low resilience using mathematical and spatial analysis approaches.
Excuse me, do you mind to speak to the microphone, because that's what they want to speak to.
Oh, I have this.
Oh, you are.
Yeah. So for our data sets, I use the resilience. For the reference resilience, I use the baseline resilience indicator for community data set, BRIC, which was created by Cutter et al. And that data set consisted of 6 domains that they used to create a composite score for total resiliency for each county in the United States. And this is a data set that we use for our reference resilience. Now, our other data sets that we use so we can get variables that we want to put in our model included sector emissions from the Vulcan 3.0, which is at a very fine resolution, which allows us to use it at the county level. And it was created by Gurney et al. We also had projected climate data that was from WorldClim and is used by the IPCC for their climate projections. So we used the mid-century business as usual scenario for those variables. And then we also had economic damages data set, which came from a study done on economic damages in the United States. Now the table on the right over here shows the different variables that came from each of the data sets that we use. So from the sector emissions, we have the airport, cement, non-road, rail, etc. From economic sector damages, we have agricultural damage, we have coastal damages, crime, and then from the climate prediction variables, we have temperature and precipitation. Now, the limitations of our analysis were due to data availability. Mostly the coastal damages and agricultural damages features had a lot of missing values for some of the counties in the United States. Now here's an image of our process and methods used in our analysis. I know it kind of looks like a lot, a little overwhelming, but I'm going to walk you through it. So we start up here with our BRIC data, and we turn it into a binary classification. From there, we merged all of our data sets together. And then after it was merged, we split the data into a testing and training data set, in which we then pre-processed both the testing and training. Once it was processed, we were able to carry out our methods of the generalized linear model, the confusion matrix, and a variance inflation factor analysis. Once those methods were carried out, we then selected our model. Now we go back to our original merged data, and we pre-process it with the same methods that we pre-processed the testing and training data. Once the data was pre-processed and we have our model selection, we input that into the logistic regression model. And once we get our probabilities from the logistic regression model, we then did a binary classification on that as well. And once we had all that data, we joined it with the county shapefile, projected it using the Lambert conformal conic projection, and then turn it into polygon to raster layers, maps for each of the features that we use in the model. And as you can see, the blocks are kind of yellowish. Those are all done in RStudio using R code. And the purple, bluish blocks are done in QGIS and ArcGIS Pro. Now for the binary classification on our reference resilience data set, we had it so that taking the scores, the total resilience scores, that if the value was above the median, then we would say that's represented as high resilience. And if it was below the median, then it would be low resilience. And then from there, we split the data into 80% going to the training data set and then 20% to the testing data set. And it was important that we split the data because we want to build our model using the training data, but then we want to see how well it does on data that's never seen before on the testing data. Once it was split, we pre-processed it first by doing the min-max scaling, which makes it so that all the features are on the same scale, and it wouldn't cause further influence on its relationship with resiliency. And then we also took the coastal damage data, and for the landlocked states, we made the NA values to be 0, because intuitively, they're not next to a coast, so they're not going to have a coastal damage, and this way we can get a better representation of the United States in our model. Now, the generalized linear model was useful because it's mostly used for nonlinear regressions, such as in our case when we're looking at binomial outcomes and using a logistic regression model. And when we get our coefficients for each of the features we input into the model, we have that negative coefficients, meaning that that variable is associated with low resilience, while the positive coefficients are associated with high resilience. And the confusion matrix was used to visualize the performance of our model and how accurate it was. And the variance inflation factor looked at how the correlations are between the independent variables. Because if they're too highly correlated, this is going to affect its relationship with the reference resilience data that we're using, affecting our model results. So we wanted all the variance inflation factors to be less than 5 for our variables. Now, the confusion matrix and the variance inflation factor were the two methods that we used to determine our model selection. Once we have our model selected, we then input that into the logistic regression model, which the logistic regression model is used for modeling the probability of binomial outcomes, such as yes or no, or in this case, high resilience and low resilience. And the equations right here are where we put our merged pre-processed data set and our model selection to get the probabilities. And once we have the probabilities from the logistic regression model, we had that if the probability was greater than 0.5, then it would be high resiliency. And if it was less than or equal to 0.5, then it would be low resiliency. Now, from our model selection, the model that we chose had an accuracy of 0.754, and all the variables were significant in the model. The table down here shows the different features that we use in our model. So this included total carbon emissions, agricultural damage, coastal damage, and total damages. We also included interactions between models, including the projected average temperature and property crime, and mortality and violent crime. And the values that you see here are the coefficients that they got from the generalized linear model. As you can see, the agricultural damage and the total damages had negative coefficients. So we'd say that they were associated with low resilience, while all the other variables had positive coefficients. So we would say that they're associated with high resilience. And the matrix on the top comes from the confusion matrix, and allows us to visualize the performance. So we had 132 data points that were predicted to be low resilience, 0, and actually were low resilience, 0 from our reference resiliency. Now this map is showing the binary classification of low and high resilience from our reference resilience data. And as you can see, a lot of the high resilience area is coming from the upper Midwest of the United States and Northeast. And this is consistent with the analysis done for BRIC, the data set where we got our reference resilience from. And the driving factors of that were due to indices that they include, contributing to social, institutional, community capital, the variables that they include for those that showed high resiliency in those areas compared to the southern part of the United States and the western part of the states. Now these show the maps of the spatial distribution of each of the features that we included in our model. If you look at the coastal damages map right here, you notice that we left the west coast as NA, that's why it's gray, because we can't represent it because we don't have any data. So instead of making those values zeros like we did for the landlocked states, as you can see in the green, we left those as 0. And the majority of the data was on the East Coast. And similarly, if you look at the agricultural damages, all these like blue spots right here, those were missing data places like counties in the United States. Now this is the map showing the low and high resiliency areas from our prediction model. Similarly to the reference resiliency map, it looks like the high resilience areas are in the upper Midwest and Northeast of the United States again, and the lower resiliency areas are in the southern part of the United States. And the gray areas are just the counties that weren't able to be represented due to missing data from some of the features that we included in our model. And what was driving this was just due to the interaction in the system in which all the different features, their relationships with each other, and also with resiliency. But it's important to note that the total damage feature was the most significant feature compared to all the other features, and coastal damage was the least significant. So that was interesting. But also that the total damage variable had the greatest weight coefficient compared to the other variables. So from this analysis, we found that total damages and agricultural damages were associated with low resiliency, while the other features we included in the model were associated with high resiliency. And using the mathematical and spatial analysis approaches, we created a model and mapped areas of predicted high and low resilience of the United States that showed the upper Midwest of the United States and Northeast to have more high resiliency, while the southern part of the United States had lower resiliency. The next steps to this project is to, instead of making the landlocked states have a value of 0, we'll impute them, which means I would take the surrounding counties that do have values to determine a value for that missing county data. And also getting a deeper understanding of the relationships and associations that the variables have with each other and with resiliency. Thank you.
Caroline, what result to you is the most surprising?
Probably that the coastal damage feature had a positive coefficient, and so it would be associated with a high resiliency because it's coastal damage, so we think that it would be negative because it's causing damages. But what really causes that is all the features that we include in the model, how they interact with each other influences the coefficient outputs that we get. So if we added more features or took a feature out, that might change the coefficient that that variable has.
Is there a way, instead of showing either low or high, to sort of get a more granular picture and maybe have more classes in between the binary to see, parse out any details you can garner?
Definitely. You can definitely do that, but since we're using a logistic regression model, which looks at binomial outcomes, that's why we had low and high resiliency.
Can you go back to, do you have a map of the brick data set on here?
This one, which is when after it's been classified.
Any other thoughts or questions? If not, thank you very much.
Thank you.